This PowerPoint is over gravity. So gravity is a field force, and that's a little bit different than some of the forces we've been dealing with. It's a field force because it acts over a distance, as opposed to being in contact like friction and normal force. So frictional force and normal force, two surfaces have to be in contact with each other in order for that force to be applied. But since gravity is a field force, then you simply have to be around in order for that force to be applied. Now there are two things that affect the amount of gravitational force. The first one being mass. Mass is proportional. So if you think of 2 times the mass, that gives you twice the force. So 1/3 of the mass would give you 1/3 of the force. It's referred to as being proportional. As one goes up, the other goes up, and the amount that it goes up is going to be the same for the mass and the force. Now, the second thing that affects the force of gravity is going to be the distance. Now, we use a little r. The reason we use r is because a lot of times the distance between two objects, one object is orbiting around the other, so that distance then becomes the radius for that object as it's orbiting around. All right, so the distance affects the force of gravity by what's called the inverse square. So let's look at an example here. If we have twice the distance, then that affects the force of gravity by the inverse square of that. So 2 inverse gives you 1/2. So if you think of any fraction, 2 is really 2 over 1. So then you flip it. We take the inverse of that, or the reciprocal of that. It becomes 1/2. And then the second part is the square. So we take that 1/2 and we square it. And whenever you square a fraction, you always square the numerator and you square the denominator. So it's going to be 1 over 4. So in effect, with twice the distance, you'll have 1/4 of the force. And that's where the inverse square comes into effect. All right, so let's do a few more examples with this. So with twice the distance, you're going to have 1/4 of the force. So if we have an original force of gravity, let's say our original force of gravity is 100 newtons. Now, if you double the distance between the two objects that have that force, doubling the distance, twice the distance, means you're going to have 1/4 of the force. So if it was 100, then now our new force is going to be 1/4 of that, which is going to be 25 newtons. So we have a force of gravity between two objects of 100 newtons, and then we double the distance, we have twice the distance, then the force will now be 25 newtons. All right, let's do another example. It says if the original force is 400 newtons, what will the force be after we change the distance by 1/3? Okay, so the first thing we have to do is we have to do the inverse square of 1/3. So 1/3, the inverse is going to give you 3 over 1, or just 3, and then that squared will be 9 times as much. So if we start with 400 newtons, the new force is now going to be 9 times as much with 1/3 the distance. So 9 times 400 is going to give you 3,600 newtons. All right, so original force of 400 newtons with 1/3 the distance, you're now going to have 9 times the force, which is 3,600 newtons. Our next example, if we start out with 750 newtons of force between two objects, and then you change the distance by 7/4. All right, so first thing we do is we take the inverse of 7/4, and that'll give you 4/7. And then we take the square of that, and whenever you square a ratio, you always have to square the numerator and the denominator. So 4 squared is 16, 7 squared is 49. So my new force is now going to be 16/49 of what it was before. Now look at this. We have 7/4, which is greater than 1. So we have a distance that's bigger than 1, so we're increasing the distance. If that ratio was less than 1, then we'd be decreasing the distance. But since that ratio is greater than 1, we have a bigger distance, and we should have a smaller force with a bigger distance. So you can see this ratio here is going to be less than 1, so we're going to have a smaller force. So now that 750 being multiplied by 16/49, that's going to give us a new force of 249 newtons. You see the force is going to decrease. With a bigger distance, you should have a smaller force. That's similar to saying that the inverse of that means that if you increase the distance, you're going to decrease the force. All right, last example here, we have a force of 800 newtons, and then we're going to have 2/9 of the distance, 2/9 of the distance. Now, because we have a smaller distance between the two, we should have a larger force. So we should expect something bigger than 800 when we finish this. All right, so the inverse square of 2/9, we take the inverse of that, we get 9 over 2. And then that squared is going to be 9 squared over 2 squared, which is 81 over 4. So that's 81/4 of our original force, and we multiply that by original force, which is 800 newtons. And you should get a force of 16,200 newtons. So if our original force was 800 newtons, and then we change the distance by 2/9, our new force is now going to be 16,200 newtons. All right, so taking these two relationships, let's look at the equation for the force of gravity. So as we said before, the force of gravity is proportional. So this little symbol here means proportional to the masses of each object. So twice the mass, twice the force. The force of gravity is also proportional to the inverse, that's the reciprocal, of the distance squared. So we take these two properties, these two relationships, we put them together into one equation. You get the masses in the numerator, and then you get the radius squared in the denominator. Now that's not the whole equation because the units on this side of the equation don't match the units on this side. So we have what's called a constant of proportionality, or what Newton called the universal gravity constant of capital G. That's going to be 6.67 times 10 to the negative 11th Newtons meter squared per kilogram squared. Now, as far as these units are concerned, you don't have to worry about that too much. The only thing you really have to worry about in this equation is to make sure everything is in base units. That means the mass has to be in kilograms and the distance has to be in meters. So if you have a distance in centimeters, you got to convert to meters. All right, and the 6.67 times 10 to the negative 11th always goes into this equation for G. It is the universal constant, so that constant always goes into the equation. So you may even want to write this equation out and always put that 6.67 times 10 to the negative 11th in there. Now the next problem here, it says that the Earth is going to be 5.98 times 10 to the 24th kilograms. The moon is 7.35 times 10 to the 22nd kilograms. The average distance between the center of the Earth and the center of the moon is going to be 3.63 times 10 to the 8th meters. So what's the force of gravity between the two? All right, so we use our gravity constant of 6.67 times 10 to the negative 11th times the mass of the Earth, which is 5.98 times 10 to the 24th, times the mass of the moon, which is 7.35 times 10 to the 22nd, and then we divide by the distance between the two, 3.63 times 10 to the 8th, and we have to square that denominator, so make sure you do that. So when you plug this in your calculator, the numerator is really not important as far as keeping the parentheses in there, but the denominator, you definitely want to put that in parentheses before you square it. All right, so we go ahead and punch that in our calculator. We get 2.22 times 10 to the 20th newtons. So that's how much force of gravity there is between the Earth and the moon. The next example, it says the sun is 2.0 times 10 to the 30th kilograms and the Earth is 5.98 times 10 to the 24th kilograms. The average distance between the center of the Earth and the center of the sun is 1.50 times 10 to the 11th meters. What is the force of gravity between the two? All right, so we use the same equation. 6.67 times 10 to the negative 11th always goes in there for your gravitational constant. And then we got the mass of the sun, 2.0 times 10 to the 30th. And we got the mass of the Earth, 5.98 times 10 to the 24th. And we divide by the distance between the two, 1.5 times 10 to the 11th. And then we're going to go ahead and put that in parentheses and square it when we divide it. And that'll give you a force of gravity of 3.55 times 10 to the 22nd newtons. So if you look at the force of gravity equation, we know that the force of gravity is 3.55 times 10 to the 22nd by the previous slide. But the question is here, what is the acceleration between the two? Because we have a force between them and nothing is preventing the Earth from accelerating towards the sun. There's no force balancing out that force from the sun. So the question is, what is the acceleration? So if you think of Newton's second law, where net force equals mass times acceleration, then you could figure out the force, use the force of gravity and the mass of the moon in order to figure out its acceleration. Another equation to use is the force of gravity equation we have. The force of gravity, the simple one we have, where acceleration is going to be on this side, mass times acceleration, mass times the gravitational acceleration is going to be equal to the force of gravity. So we take that force of gravity, we divide it by the mass of the Earth, and that's going to give us an acceleration 3.55 times 10 to the 22nd divided by the mass of the Earth. You put that in parentheses if you need to write this out as 10 to the 24th, and we go ahead and divide those, and you get 0.0059 meters per second squared. So what is that acceleration? Are we actually accelerating towards the sun? And the answer is yes. The Earth is accelerating towards the sun. However, let's be careful. It's not moving towards the sun. There's a little bit of difference that you have to understand here. Accelerating towards the sun and moving towards the sun are two different things. Our acceleration is towards the sun, but the Earth is moving in a circle. It's not a perfect circle, but it's pretty close to being a really, excuse me, a really good circle. And this acceleration is actually the acceleration that is causing the centripetal acceleration. It's what keeps us moving in a circle around the sun. So that acceleration is centripetal. So yes, we are accelerating towards the sun, but we're not moving towards the sun, because we're moving in a circle. All right, so if we use the two equations, we have this equation here for the acceleration that we just used to find the acceleration of the Earth towards the sun. If we use the big equation for gravity, there's something interesting that happens here. So we take that gravitational constant, 6.67 times 10 to the negative 11, times the mass of the sun, times the mass of the Earth, divided by the distance between the two objects squared. So that's the force of gravity equation there, the big one. But then if we divide by the mass of the Earth like we did here, then we find our acceleration does not depend on the mass of the Earth. And what we get is we get the gravitational constant, 6.67 times 10 to the negative 11th, times the mass of the sun divided by the distance between the two objects squared. Now, what's interesting about this is if you don't need the mass of the Earth to figure out its acceleration, then what about the Earth itself? If we're at the surface of the Earth, can we figure out its acceleration without knowing what object is on the surface of the Earth? And the answer is yes. So if you use the gravitational constant, 6.67 times 10 to the negative 11th, you use the mass of the Earth, 5.98 times 10 to the 24th, and then you divide by the radius of the Earth. So any object on Earth is going to be at its surface. So the radius of the Earth tells us how far apart the center of the Earth and that object is going to be. So 6.38 times 10 to the 6, and then that quantity is squared. What you should get is you get something like 9.799 or something like that. So it rounds up to 9.8 meters per second squared. So with that, we have the acceleration due to gravity. So if you ever wonder why we always use the acceleration due to gravity as 9.8 meters per second squared, regardless of what object you're talking about, it's because of this equation right here, because the acceleration due to gravity is dependent on two things. That is the mass of the Earth and the radius of the Earth, and that's it. So the mass of the object as it's falling does not determine how much acceleration it's going to have. But then our question comes up, well, what's the mass of the Earth? 5.98 times 10 to the 24th? How do we know that? How do we know the mass of the Earth based on this? And that's the next question we're going to answer.